another type of billiards. These are so-called neutrino billiards. I mean, yesterday I already mentioned them in my colloquium talk, and I will especially speak about billiards with a shape which would be boring when you look at the corresponding non-relativistic one, but when these have some interesting features. So I mainly will talk about such systems and also give some examples of chaotic ones with interesting properties. So, I mean, coming back to the conjectures by Berry and Tabor and Bohigas, Giannoni and Schmidt, these were stated in the context of non-relativistic quantum chaos. Just to repeat, according to the Berry-Tabor conjecture, the eigenvalues of typical integrable systems behave like random uncorrelated numbers. So when you look at the statistics, you can compare to the statistics of random numbers drawn from a Poisson process. On the other hand, if you have a billiard with the shape of a chaotic system or generally a quantum system with whose corresponding classical counterpart is fully chaotic, then according to Bohigas and Giannoni and Schmidt, you will find agreement of the spectral fluctuation properties with those of random matrices from the Gaussian ensemble. So today I will basically, some problem or, oh, so I can talk, I will continue, yeah. Okay, so I will just, in my talk, I will basically speak about Gaussian orthogonal ensemble and Gaussian unitary ensemble. And yeah, now the question arose whether these conjectures apply to relativistic quantum billiards like these neutrino billiards. So there, the one problem is that you don't have a well-defined classical limit for neutrino billiards, so one has to look at use methods which are applicable in the semi-classical limit, like length spectra and Hosimi distribution. So that's what I will talk about today. So first of all, how did we come to neutrino billiards? I mean, it started with our experiments with Dirac billiards, about which I spoke yesterday. I mean, they are used to simulate properties of graphene. And graphene has a property that depending on the energy range, you will either find properties of a non-relativistic system or around the these conical touch points. The properties are well described by a Dirac equation, so two-dimensional Dirac equation for the two components here, the corresponding to these two triangular lattices. I mean, the hexagon lattice is formed by two triangular lattices which are intermingling, and this property leads to this interesting band structure of graphene. And I will now show that similarly in neutrino billiards you will find properties which are related to this additional spin degree of freedom. So these are interpreted as quasi-spins in a graphene billiard, and something similar you can do in the neutrino billiards. So I mean, to get a graphene billiard, what you have to use is a so-called tight binding model. Tight binding model because you only include couplings to nearest neighbors. Usually you just include couplings to nearest neighbors. This is already sufficient to get a chaotic dynamics if you choose a shape of a chaotic billiard. Or in our, I mean, for the description of the experiments, we also use second and third nearest neighbor coupling. So it's a very simple model. What you have to do to get the eigenvalues, you just take a matrix which has a dimension of the number of sides of your graphene billiard and diagonalize it, and then you have the eigenvalues for the whole energy range. So here I just show two examples. So the resonance density for a graphene billiard with a rectangular shape and one with the Africa shape. I mean, the black one was obtained in our experiments, but it's similar for when you do the computations for the graphene billiard. And the sweat curve is just obtained by smoothing the density of states using, instead of a sum of delta functions, a sum over Lorentz curves. So you get this structure by simply diagonalizing this graphene billiard matrix, this tight binding model matrix, which I mean it only depends on, here in this case, on first, second, and third nearest neighbor coupling. There you don't have a symmetry with respect to the Dirac point. This you can see Here you have an asymmetry. And you would have a completely symmetric one if you only use first-order couplings. So, but the density of cells looks the same for both, but when you look now at spectral properties, then you find exactly what you find in a quantum billiard. So here for the Africa billiard, here I just show ratio distributions again. I mean, these are ratios of adjacent spacings, nearest neighbor spacings, and these are dimensionless quantities. Therefore, you can, I mean, to unfold, you would need to extract this frequency dependence of rho of f. So if you use now the ratio distributions, you don't need to. You can just take the eigenvalues, but you have to make sure that you don't get problems with these singularities. But for the number of eigenvalues which we used, we didn't get problems. So then we computed the ratio distributions. These are obtained by just summing over all the 2,000 eigenvalues. And then you get a very good agreement with Poisson for the rectangular one. So this is ratio distributions between for the ratios of adjacent spacings. And this is for the ratios of spacings of next nearest neighbor eigenvalues. So here, that just to remind you, I mean, I showed it already yesterday. So, and these results, which we obtained with the Dirac billiards, graphene billiards, were the motivation to look also at properties of neutrino billiards, because, I mean, they are described by Dirac equation, which has exactly the same form as in a graphene billiard, where you then would set here, replace V by boundary conditions. So V is a potential which couples these parts here, and in a neutrino billiard you have here V equal to 0, but you confine your billiard, your spin 1/2 particle to the billiard region by imposing boundary conditions. So this would be the analogy to this, what is called here potential. So one important thing is that when you have a neutrino billiard with chaotic dynamics, then you don't get GOE, even though you don't add any magnetic field or nothing, you don't need to add anything, you will get GUE. And this exactly was the motivation of Berry and Mondragon to study these systems, because they saw GUE statistics without that you need to apply additional magnetic field. I mean, usually when you have a quantum billiard, a conventional one, to get time reversal invariance violation, you need, for example, to apply a magnetic field. That's one way to get time reversal invariance violation. And this is not needed when you look at these neutrino billiards. So the Dirac equation can be written in this form. This term is exactly that one here, expressed in terms of the Pauli matrices sigma x and sigma y. And then you have a mass term here, which will correspond here to the V. So it's replaced by a mass term in this massive Dirac equation for massive spin 1/2 particles. I mean, Berry, he introduced these billiards for massless spin 1/2 particles. And I added this mass and could use his results and extend them to massive ones. So this is what I will explain now. So the boundary condition which is imposed on the spinor wave functions is that outgoing current should vanish. That is the normal vector. This is the current. It's obtained by taking here the gradient in p direction, then this is exactly equal to sigma times this part here doesn't depend on p, so there you would get here a sigma, and then if you look at the expectation values, then you multiply it from left with a psi dagger and from right with psi, and the normal component of this current has to vanish, and that's a boundary condition. That is when here I just show one example, I will show more. For the current in a rectangular billiard, so it has no normal component along the boundary. And thereby, the spin 1/2 particle is confined to the billiard area. And this can be expressed in this form. So when you evaluate it, you can express it in this form. Here I use coordinates in the complex plane. So x coordinate and y coordinate are written in the complex plane. Then the y-axis would correspond to the imaginary axis in the complex plane. And the normal vector, it's given here by cosine alpha sinus alpha, where alpha is the angle between the normal vector and the x-axis. So, and this is exactly this term here in complex plane representation. This is a normal vector. And this boundary condition now couples psi1 and psi2 via such a phase. And this phase depends on S. And as I will show, this has consequences on the properties of the neutrino billiard. So they are not, I mean, when you look at a chaotic one, you get similar results as for a quantum billiard, but when you now look at billiards with an integrable shape, then you can get completely different behaviors, as I will show now in this lecture. So, and usually I use polar coordinates, so I won't mention it explicitly, but in polar coordinates, then the boundary is described by this W of R and phi at R equal to R naught. So the domain is for R less than R naught, and phi is an angle variable which varies here from 0 to 2 pi. And it can be re-expressed in terms of the arc length. Arc length is given by the integral from 0 to phi, W prime of phi tilde d phi tilde. So this parameter S, which is the one which I introduced in the context of quantum billiards. There you usually, when you look at the Poincare surface of section, you look at the perimeter. Position is defined in terms of the perimeter S, and momentum then in terms of the reflection angle at the boundary. So that so ds is just given by W prime of phi d phi. So this term you will see in the formulas which I now give. So now for massive neutrino billiards, one has an energy can be expressed in terms of a parameter beta, which is given by the rest momentum, rest mass momentum divided by the free space momentum. And when this parameter goes to infinity, then you go to the non-relativistic limit. And you can show that this, taking this limit, it complies with the boundary conditions. That is, you have the same boundary conditions, but they will change according to this formula here, which I will come to. When you take beta to infinity, beta is this parameter, beta times k is the rescaled mass in a sense. So you keep h bar fixed, c fixed, and vary the parameter mc over h bar by varying mass. And that's how you can get the non-relativistic limit. So to that one I will come. And when you now replace the wave functions by wave functions where you multiply the components by these terms, then this is a common procedure from relativistic quantum mechanics. So when you multiply them by these terms here, where sinus theta beta is beta divided by square root of 1 plus beta square, so beta was this parameter. Now in the non-relativistic limit, you have here theta beta equal to 0, pi over 2. And in the ultra-relativistic limit, you have theta beta to 0. Because non-relativistic means that this goes to 1, and ultra-relativistic means that you choose mass equal to 0. So then the mass parameter is replaced by this angle theta beta. And now if you now write down the Dirac equation in terms of these components, then you can separate it and you get a Dirac equation which is exactly identical in form to that of a massless particle. So I could use all the results which were obtained by Berry and Tabor for the boundary integral and quantization conditions. I could then simply extend to massive neutrino billiards. The only difference is now the boundary condition, which now depends on this parameter k. This is a ratio of 1 minus sinus theta pair divided by 1 plus sinus theta pair sinus beta. So it's equal to 1 when in the ultra-relativistic limit. And then you get back the boundary condition which I just wrote down on the previous view graph. And when you come to the non-relativistic limit, so then it goes to 0. So in the non-relativistic limit, one can show that then the components decouple, psi1 and psi2 decouple. I mean, they're coupled via these boundary conditions. They then decouple, and psi2 goes to 0, psi1 has a finite value, and it obeys then boundary conditions. This can be explicitly shown. So when you take now in the non-relativistic limit, you come to the quantum billiard. And I will show some examples for the boundary for spectral properties. They then also change into properties for the quantum billiard. So so the Reich equation then has the same form as for mass equal to 0 when you do this change. And to get back the original components, you just have to multiply with 1 over these prefactors, and then you get the solutions for psi1 and psi2. Now, generally, if the shape is equal to that of a chaotic billiard, then you expect Gaussian unitary ensemble because the Dirac equation violates time reversal invariance. I mean, these are complex entries in the, when you go back, here you have this is a complex valued structure because P is I times gradient, minus I times gradient, so you have here a complex Hamiltonian which violates time reversal simply because it's complex. And also the wave functions are complex then. The solutions, the spinor eigenfunctions are complex. So now to obtain the eigenvalues of neutrino billiards, I use a boundary integral method which was introduced by Berry. I mean, the starting point is the Green theorem. So you combine the Dirac equation with the matrix equation for the free space Green function of such for relativistic for spin 1/2 particles is given in this form. So here you have the same Hankel function as in the non-relativistic case, but here you have this additional term. You have to apply it to this H0, and then you get the corresponding Green function for relativistic neutrino billiard. I mean, yesterday, Martin already introduced it for non-relativistic quantum billiards. And you basically have this term here with a minus I over 4. And the boundary integral, it's exactly the equation, has exactly the same form as that which yesterday Martin introduced. But here one now has a 2 by 2 spinor component. So a spinor matrix is the Pauli matrix is multiplied with the Green function, which is a 2 by 2 matrix, and these spinor eigenfunctions are 2 by 2, so two-dimensional vectors or whatever. So they have two wave function components. Now when you write down this term here is on the boundary, and to this term here, so there's this equation with this part here, here you can insert now the boundary conditions because it's an integral along the boundary. This part is an integral along the boundary, and this here is a wave function along the boundary. And it's not Dirichlet, so you get some non-zero terms here. And if you insert them, then you get a boundary conditions in terms of boundary integrals for the two wave function components for psi1 and psi2. So you have essentially two boundary integral equations, but these are in a sense identical because you can get from this boundary condition for psi2, you can get back to that for psi1 by simply inserting the boundary conditions. So you can choose one of them and solve them, and then you get the eigenvalues. And then to get the eigenfunctions for the two components, you can put back into the first equation. Then you get the eigenfunctions. And the eigenvalues are obtained by solving either this boundary integral equation or that one. However, there's a problem. I mean, here you have this term here. This is just direction of the difference vector between 2 points of impact. So this is the vector rho, and rho divided by the absolute value then gives you this e to the I psi in complex plane representation. And rho is the distance between the 2 points of impact inside. So when you go from one reflection point to the next one. Now, these have like yesterday, I mean, like Martin pointed out yesterday, H0 and H1, they have singularities. I mean, H0 has a logarithmic singularity when you take rho to 0, and H1 has a 1 over rho singularity. So one has to, before one can solve these integrals, one has to get rid of these singularities. And this is done by, I mean, to do this, one can follow Berry. So what Berry did, he replaced the wave functions along the boundary by a combination of the wave functions. So this is psi1 And this is minus I times e to the minus I alpha of s psi 2 of n and s over 2. Here n and s are now coordinates in a moving coordinate system. It moves along the boundary. And s then is the x-axis then corresponds to the tangential vector along the boundary, and the y-axis would correspond to the direction of the normal vector. So this is a moving coordinate system, and in that one we use these wave functions phi 1 and phi 2, which are combinations of psi 1 and psi 2, and when you take the limit from the interior to 0, then you get back the wave functions themselves, the wave function components along the boundaries themselves. And this you can see by, this is exactly the boundary conditions when you take n equal to 0, which would correspond to the origin. So then you get back the boundary functions. So when you now combine them, and so what you do essentially, you add these two equations, and then you get, in the massless case, then you get an integrand which doesn't have any singularities. And if you have, in the massive case, you have to do a bit more. So you have to use another relation. So this is a relation which I derived by using these boundary integral equations. And then you again get an integral which doesn't have any singularities. Here, this is here you have to take out the case phi equal to phi prime, because it's here on the left-hand side. Phi equal to phi prime is the problematic point where you would have singularities when you use the original version. And then to get the eigenvalues of a massive or massless, massless would mean that you have here a 0, and here you can integrate over the whole space, because then you don't have any singularities. And for massive ones, you can also use this equation and then obtain the eigenvalues of the massive neutrino billiard. So the integrand now looks a bit more complicated than before, because here you have a sum of H0 and H1 again with these prefactors, and these prefactors make sure that you don't have a singularity. So here so yeah, one I mentioned already on the first lecture. So when you look at these wave functions, you can show that they obey Robin boundary conditions. So you can write them down. That's what I'm doing here. So these are exactly these wave functions, boundary wave functions, which I introduced before. And you can show that they fulfill Robin boundary conditions. So you have here normal derivative, and here you have the wave functions themselves. Here beta tilde, it's equal to beta times k, so mc over h bar, this part here. And this part is a curvature at the boundary. So there you then get back, and these are fulfill Robin boundary conditions in this form. I mean, Martin introduced it yesterday, and I think this term didn't depend on the S parameter there, or as far as I remember. Whereas in our case, it depends on the position, the curvature along the boundary. So here I just show one example for the half circle. I mean, to see what this would look like. So here are wave functions for varying beta tilde. So when you have beta tilde equal to 0, then this term approaches Neumann boundary conditions. When in this case, curvature is equal to 0 along these boundaries. That is, for the half circle, it approaches Neumann boundary conditions for beta tilde equal to 0. And when you increase beta tilde and come to very large values, then this term here will survive, and it's so it will be much larger than that one. And in order to get finite size contributions, then this term here would fulfill Dirichlet boundary conditions. So it interpolates between Neumann boundary conditions and Dirichlet boundary conditions, and you can show that then the second component of the Spinor eigenfunctions is equal to 0. So here I just show the results. I mean, the magenta one, it's Dirichlet, and the Neumann one is Neumann boundary conditions, and we change the values of beta, and then you get something which is between Dirichlet and Neumann, but it's always close to Poisson in all these cases. And this is important because later I will show that for the neutrino billiard, half-circle neutrino billiard, you will find GOE. So so that was the reason why we looked at this, because we wanted to see whether you can also create GOE by looking at a half circle with these Robin boundary conditions, but that's not possible. So that was essentially shown by Berry and also Bogomolny. When you take a full circle with Robin boundary conditions, then you always get some spectral properties which are close to Poisson, but not GOE, like we get for the neutrino billiard. So here I just show symmetric solutions, but that's not so important. So I also derived a trace formula for massive neutrino billiards by following the same recipe as was introduced yesterday by Martin. So I followed his works. It starts from the boundary integral method, and then you can write down the fluctuating part in terms of the sum over trace of q to the power of p of k, and this corresponds then to these integrals, p integrals along the boundary. And so I just followed his procedure and then obtained a trace formula, which again contains the terms which you would have in the corresponding non-relativistic quantum billiards multiplied with some additional phases. So here. And I mean, I must say it's a very badly converging sum. You have to exclude certain terms, these grazing orbits, in order to get convergence of the series. So it's not so nice. But so here, for example, when you have a billiard with chaotic classical dynamics, then these are exactly the amplitudes and phases of Gutzwiller's trace formula. So what one has to do, one has to determine these terms. These are well known, so in terms of reflections at the boundaries, in terms of periodic orbits, and multiply them by the contributions from Gutzwiller. One can also take the limit beta to 0. So in the non-relativistic limit, you get back the Gutzwiller's trace formula for the quantum billiard. When you take limit beta to 0, then you get this trace formula. So it's again Gutzwiller or the entries of the trace formula of the corresponding non-relativistic billiard multiplied with a phase. So this is a total phase which is accumulated when the particle moves along the boundary, along a periodic orbit. I mean, the sums are all only over periodic orbits in the end. So this is a sum over periodic orbit. This is a total phase which is accumulated along when the particle travels once along a periodic orbit or several times. And then you have this additional term. And this is a big difference between non-relativistic and relativistic quantum billiards, because as you can see, when the number of reflections of the periodic orbit as a boundary is an odd number, then you don't have any contributions. So these are missing when you look at the length spectra. You only will see peaks which correspond to an even number of reflections at the boundary. So this, I mean, I will show some results during the talk. So I just wanted to mention here, and now I will start with some examples. So for example, when you look at a simple, this is the most simple system you can have is a rectangular billiard. So the left one, I showed it to you already several times. So this is a quantum billiard, and this is a corresponding neutrino billiard. And as you can see, it has a very complicated structure. It doesn't have this chessboard structure, and the reason is this additional spin degree of freedom, which completely changes the properties of such system. Can change. I mean, in this case, it doesn't change the spectral properties, but it has some other changes. And here I show the corresponding current. I mean, when you look at the current, you see that the normal component vanishes, and this means that I didn't make any mistakes in computing. You always have to make sure when you're looking at numerical errors that the normal component of the current along the boundary is 0 or small compared to the relevant quantities. Yeah, these are regular. I mean, this is a rectangular neutrino billiard, so depending on Whether it's regular or not regular, you cannot tell from the boundary, as I will show to you now. So it's not like in a quantum billiard. When you have a rectangular quantum billiard, you have two constants of motion, and you know that the statistics is Poisson if it's a perfect integrable system. I mean, there you also will see deviations from Poisson, because I mean, the quantum numbers are just square root of n square over a square plus m square over b square, so these are not Poissonian numbers, so you would have to take a very large number to get something close to Poisson. Whereas in this case, I mean, in this example, as I will show, you will find Poisson statistics, but in other examples that I will show now, you don't have it. So you cannot, from the shape, you cannot tell whether the spectral properties are Poisson or something else when you look at billiards with an integrable boundary. And all this has to do with one properties of neutrino billiards, namely you cannot separate wave functions by mirror symmetry. Like here, for example, here you can separate, like this one is symmetric along the two mirror axes, whereas when you plot these, here I plot them as an absolute value, but when you plot each component separately, then you will immediately see that you cannot separate the spinor eigenfunctions anymore according to their mirror symmetries. And this has to do with the following. I mean, generally, when you apply orthogonal transformation to the location vector R, then this corresponds to transforming the Dirac equation by using a unitary operator, which corresponds to this orthogonal transformation. And then the wave functions are obtained by multiplying with this unitary operator. And this depends on what kind of symmetry transformations you are doing, I mean, geometric transformations you are doing. For example, reflection at the x or y axis is plus or minus sigma z. And then the corresponding unitary operator for x, when you reflect along the x-axis is just sigma x. When you reflect along the y-axis, it's I times sigma y. And then you can write down the corresponding wave functions of the transformed Dirac Hamiltonian. And you can show that if psi1 and psi2, so psi1 tilde, psi2 tilde, if they obey boundary conditions, then this is not the case for the reflected one solutions. So you don't have, when you transform now, then you won't find they don't fulfill boundary conditions. And this means that you cannot separate by mirror symmetries in this case, simply because boundary conditions do not comply with this reflection transformation. On the other hand, you can find some other symmetries, because you can show that when you change x by minus x in the Dirac Hamiltonian, then you get the complex conjugate of the Dirac Hamiltonian for neutrino billiards, and then you will find some symmetries in this. It's not a symmetry because here you have your wave function, here you have the complex conjugate wave function, but you will find such properties that if you change from x to minus x, then you change to psi minus star or minus psi minus star, or when you reflect from y to minus y, then you would have these transformation properties. Like you always have to consider both components. So here I just show one example is an ellipse. I mean, ellipse, it has two symmetries along x and y axis. And so here I show the real part of psi1. This one is anti-symmetric with respect to x and y axis, but the imaginary part is symmetric with respect to the x-axis and symmetric with respect to the y-axis. So they have different symmetry properties under reflection. And the same for psi2, it's also different from that one. So here you have a symmetric along the x-axis, but anti-symmetric along that axis. And this has to do with these. So in this case, you have such a property. And you can see here, but what it has. So it doesn't have reflection symmetry, but it's symmetric under rotation by pi. I mean, if you rotate from this point to that one, then you come back to the original one. Or when you rotate this one with respect to there, then you again have something which is symmetric under rotation by pi. So both components are symmetric under rotation by pi, and these are both anti-symmetric under rotation by pi. So you have a rotational symmetry, but you don't have mirror symmetries. And this I use, and I will show now what you obtain when you consider such symmetries in a rectangular billiard, for example. I mean, generally, when you have a shape with an n-fold rotational symmetry, then this means that you can rotate the shape by 2 pi over n, and you will come back to the a point which is exactly this. So you won't change the shape of your billiard by doing a rotation by 2 pi over n. If you have an n-fold rotational symmetry, and the corresponding unitary operator which performs the transformation of the corresponding Dirac equation is simply given by this matrix here. Now you can show that such a transformation, it complies with the boundary conditions. That is, if you find solutions, then these are also solutions when you rotate now by 2 pi over n. So you will have solutions, and these solutions can be like in the non-relativistic case, like I explained 2 days ago. You can separate according to the transformation properties. So when you rotate by 2 pi over n, then you will get here an additional phase factor multiplied with the original wave function component. So this is exactly the same as in the non-relativistic case, as long as you consider each component separately. So for each component separately, you can classify like in the non-relativistic case. But the difference is that the first and second component, they transform differently under rotation by 2 pi over n. For example, if the first component is from the class L, then the second component is from the class L minus 1. So you have essentially an intermingling of rotational symmetries, because both components transform differently. That is, the full spinor eigenfunction is not rotational invariant, because each of its components transforms differently. So this is, for example, here I show for the triangular billiard, so here one can derive exact analytic solutions for. I mean, I derived it I don't know, 2 years ago maybe. So there you can get exact analytic results for the eigenvalues in terms of this matrix K and the angles, theta, eta. So you have to fulfill these conditions, and then you get the eigenvalues. Theta K is simply the angle between k-axis and x-axis. So, and here I show some examples for L equal to 0. You have rotational symmetry in psi1. I mean, L equal to 0, it's like in the non-relativistic case, you don't have a phase. That is when in the it's rotationally symmetric. So as you can see here, when you rotate by 2 pi over 3, you always come back to the same point here. On the other hand, so this is a real part of psi1, this is a real part of psi2. It doesn't have rotational symmetry, but you have to move by a whole, so by pi to come back essentially. It has L equal to, this has L equal to 0 symmetry, then this has L equal to 2 symmetry. So whenever this is rotational invariant, this is not rotational invariant, that is, the spinor eigenfunctions cannot be, they are never rotational invariant when you consider both components. And here, for example, psi2, here psi2 is rotational invariant, and this one has symmetry class L equal to 1. So this is just for illustration. So here you also get a quite complicated structure. Here I show the current, absolute value of the expectation value of the current, and also the phases. So it's always unidirectional along the boundary. When you choose boundary conditions, as I showed to you, then it always moves clockwise along the boundary. You can also use the other sign, we'll show results later, then it would always move anti-clockwise. Entanglement in the sense that both components have different symmetry properties, and this will become visible when you take, for example, when you take the triangle and now cut it along this rotational symmetry class into 3 parts. Then you will entangle the symmetry properties, and this can lead to chaotic spectral properties of a typical chaotic system. because you mix different boundary conditions essentially. Another question? Or? So, and here, generally, as I mentioned, you can, again, separate by symmetries before diagonalizing. So that's what I'm always doing, because then you have much less work with diagonalization. You can get 3 times more eigenvalues than in the case where you don't separate. And this is done exactly the same way as I explained for the non-relativistic case. I mean, you start from the boundary integral equation. Now you use symmetry properties. I mean, symmetry property means, in this case, you have a 3-fold symmetry. So when you use the boundary function and rotate it by 2 pi over 3, then you get the same boundary functions essentially. So when you go from here to here, you have exactly the same shape. So it's rotational invariant, and this can now be used to here in the integrand, which is this sum of the Hankel functions H0 and H1. And then you can use this symmetry to reduce the integrals to integrals over 0 to 2 pi over 3 and separate them by symmetry classes. And then in the end, you will get such a boundary integral for each symmetry class separately. Here I have it, I wrote it down for the full system, which you obtain from here by separating into integrals from 0 to 2 pi over 3, so 2 pi over 3 to 4 pi over 3, and so on and so on. And then when you do that, then you would get boundary integral of this form, and this is the shape of the matrix which you obtain when you now restrict phi and phi prime to 2 pi over 3. And to get the symmetry projected boundary integrals, you have to bring this to block diagonal form, and this can be done with a unitary transformation explicitly. And then you get, in the end, symmetry projected boundary integrals for each symmetry class, where this is a sum over lambda equal to 0 to 2 of these matrices which are defined here. And these matrices are given essentially by these Q matrices. So I didn't write them down in detail, but this you can find in the publications. These are simple integrals which essentially have the same form as the original one with Hankel functions H0 and H1, but you have to use symmetry properties. So it will be a sum over 3 terms like here. So this can now be used to obtain the eigenvalues. And here I show some results. I mean, this I showed already yesterday. For example, when I use this shape, I mean, this is exactly the same shape as the shape of this microwave billiard, which we used like 20 years ago to get the eigenfrequencies of the corresponding microwave billiard, that is the eigenvalues of the quantum billiard. So we use exactly the same shape, so you can compute eigenvalues. Here I computed like, I think here I show results for 1,500, but I had more. So for m equal to 0, for different masses, for m equal to 0, m equal to 20, m equal to 100, and when you go in this direction, then the wave functions get more and more similar to those of the corresponding non-relativistic billiard. But here you can see the property, I mean, psi1 and psi2 are complex wave functions, so you don't have any, I mean, here it seems as if you have nodal lines, but you don't have any nodal lines. This is a bit, it looks, you don't see any structure usually when you look at them, and here my student used some special coding. So it looks as if you have nodal lines, but generally it looks like here in this case, or like in these cases. And then when you increase mass, then they will become more and more real, and psi2 will vanish when you come to sufficiently large values. So in here I show results for the spectral properties. I showed them already yesterday. I mean, for increasing mass, m equal to 0 is the ultra-relativistic limit there. You are always close to GUE, independently on whether you look at singlets. I mean, when you have a quantum billiard, singlets have GOE statistics, doublets have GUE statistics, and in the corresponding neutrino billiards, you would always expect GUE for the massless case, so in all 3 cases. So this is one way to distinguish between a quantum billiard and a neutrino billiard by simply looking at the statistics. And with increasing mass, they move more and more to the solutions for the corresponding quantum billiard. These are shown in blue. However, here we had to extract contributions of this short periodic orbit. Here you have a triangular orbit, which leads to deviations in sigma 2. I think one of you asked me about it when I showed number variance. So this is one of those short orbits which lead to deviations in sigma 2 when you plot it like here. This is obtained when you include this triangular orbit, and when you extract it, then you get agreement with GOE. So here one has to extract contributions from non-universal orbits in the sense as they don't show the chaotic behavior. I mean, these are just triangles which move back and forth like the bouncing ball orbits in the stadium billiard. Again. Yeah. So you have blue is quantum billiard, and cyan is what you obtain when you remove the contributions. Then you get perfect GOE. And also the same for GUE. So this is one result for neutrino and quantum billiard. I mean, there essentially they behave similar, with the only exception that for neutrino billiard you don't get GOE but GUE. Generally, when you have a shape with which corresponds to a chaotic billiard. So here I also show some length spectra with increasing mass for here the neutrino billiard. Here I use all eigenvalues. When you increase the mass, then you will move more and more to the length spectrum of a quantum billiard. I mean, this is exactly what is also expressed in the Straits formula, that if you take the limit of mass to infinity, then it will move towards the length spectrum of a quantum billiard. Whereas for the massless billiard, you have peaks that are missing, and these correspond to lengths, to periodic orbits, which have an odd number of reflections at the boundary. So these are missing. So here you see it in the lower part, and there this one, for example, is missing. So you know that this one corresponds to an orbit with an odd number of reflections. So, or here are some missing. And here we separated also by symmetry class. So for singlets, you see, I mean, this is for the neutrino billiard, and when you compare with that one, you see that there are additional orbits here in these parts, depending on, on mass. So, and these are orbits which are so-called pseudo-orbits. These are periodic orbits as long as you remain in the fundamental domain of the corresponding symmetry class. And they will cancel out each other when you sum over all of them, and then you get these results here. So when you sum over all of them, and here I show it as function of mass, the singlet. So when you sum over all symmetry classes, so also add the results for a duplet, then you will get the result which I showed for the full quantum billiard or the full neutrino billiard. But here you again see additional orbits. These are pseudo-orbits which would disappear when you now sum over all symmetry classes. And you can also, to identify pseudo-orbits, you can see that some are not here, but then they appear. So this is what, the reason there could also be that it's a periodic orbit which corresponds to an odd number of reflections. But you see other orbits which vanish when you take the limit of mass to infinity, and these are for sure pseudo-orbits that are present in the neutrino billiard but not present in the corresponding quantum billiards. So the pseudo-orbits don't have any agreement with those of the corresponding quantum billiard, must not have, because you have different boundary conditions along the fundamental domain boundaries. Now I come to another system. I mean, I showed you results for the rectangular billiard, and an even simpler system is a square billiard. So here I show wave functions. Here again, you have a fourfold symmetry, because the lengths of all sides are the same. So your rotation by pi over 2 then leads to the back to the original boundary. So here you have a fourfold symmetry. That is, you can separate into L equal to 0, 1, 2, 3 in that case. And here I just show some examples for wave functions, real part, imaginary part, real part of psi1, real part of psi2. They behave differently under symmetry transformations, as I explained. And also, when you look at the momentum distribution, if you have one k value, which gives you the eigenvalues, then you would see one spot here. So the localization is at square root of kx squared plus ky squared. And if you have, like in a square quantum billiard, you would see something like that. Just 8 dots, which correspond to the kx absolute value and ky absolute values. However, in relativistic neutrino billiard, you don't see such spots. You see more or less continuous distribution along the radius. The radius gives you the value of k, which is square root of kx squared plus ky squared. So the momentum distributions are localized on the value of the radius, which corresponds to the value of k. So the radius is equal to k, to the eigenwave vector k. And here you see, here you have something which you would find in the corresponding non-relativistic billiard. Exactly 4 spots which correspond to kx. Here you have ky equal to 0 and kx equal to k. Here you have kx equal to 0 and ky equal to k, and this is would be a simple bouncing ball orbit essentially. And here I also show the currents which contain information of both wave function components. Therefore, I usually don't show wave functions but just currents because they contain the information of psi1 and psi2. So that when one now looks at the spectral properties, so I separated now by symmetry. So by twofold symmetry in that case. So then you can see the spectral properties of the full neutrino billiards. They are overshooting here because you have additional accidental degeneracies, and I didn't take them out. Then you have this kind of overshooting here. Also here you see that it goes beyond the curve for Poisson. Poisson is just a straight line equal to L, or here L over 15, and here you see an overshooting which I can remove by simply removing those accidental degeneracies. And however, for the symmetry projected one, I always get very good agreement with semi-Poisson. Here, this is a nearest neighbor spacing distribution. The dashed line is the expression for semi-Poisson. What does semi-Poisson mean? You take a series of Poissonian random numbers and you take out every second one. Then you get semi-Poisson. And it has completely different properties than the full Poisson system. So this would be for when you take the whole Poissonian random number sequence, and the dashed line is the one which you obtain when you take every second one of a Poissonian random number sequence. And this is called semi-Poisson. And I find agreement now for the symmetry projected eigenvalue, eigenstate. Symmetry projected means that I separate into the 4 symmetry classes, and then I get agreement with semi-Poisson. Here also up to a certain point, then you see saturation. So to see agreement up to longer values of L, you would need to add more and more eigenvalues. And here I show also ratio distributions. So for ratio distributions, you don't need to unfold. So the symmetry projected all lie well on the curve for semi-Poisson. Here I show the results for the full system. For a quantum billiard, it's non-typical. So it has these gaps. You see, when you look at the nearest neighbor spacing distribution, I don't show it here because it's really ugly. It has gaps in between because, I mean, the corresponding quantum billiard, it's just, I mean, a simple expression for the nearest neighbors, which will never be Poissonian. So you can show that the long-range correlations, when you take sufficient number of eigenvalues, they will approach what you expect for Poissonian random numbers, but nearest neighbor spacing distributions, you find big gaps like here. And here I show for the corresponding symmetry reduced one, which would be a triangle with inner angles pi over 4 and one angle pi over 2. So that would be Poisson, so the corresponding triangle. So in this case, we find semi-Poisson for the symmetry projected. And length vector here I show again. I mean, there you see only peaks which correspond to length of the neutrino billiard, the full quantum billiard, and also you see here peaks for the symmetry projected one. You only see a few peaks which correspond to the length of pseudo orbits, like here, for example, you see some. And also, I mean, since the number of reflections is always an even number, the length spectrum of the neutrino billiard and that of the corresponding quantum billiard, they show peaks at the same length. So now I come to the rectangle. So here again plot the real part, imaginary part of psi1. And then you can see again that they have differing properties. In this case, you have a two-fold symmetry. That is rotation by pi will either lead to the wave function itself or minus the wave function. So it's, I mean, it's a weird way to separate a rectangle according to symmetry classes, but one usually does when I have a quantum billiard, one would separate by mirror symmetries. And that's not possible in a neutrino billiard, so therefore I decided to separate by the rotational symmetry. And then I got these results, which I will show now. I mean, here you can, these are just some examples where you can see that they don't have a simple chessboard structure. I mean, if you take the absolute value, then you won't see any, so square of this plus square of this, then you don't see any nodal domains. And the currents also, they can look very complicated. I mean, you see some which are similar to what you would expect in a quantum billiard, but generally the structure is much more complicated. And the spectral properties in this case, I mean, here I show one result. This is a rectangle with the golden mean, ratio golden mean, so it's as irrational as possible, B over A. And here I show an example. I don't think, oh no, I don't show the example. I also did same studies with B over A equal to some rational numbers there for the neutrino billiard. You find good agreement with with Poisson. So here this is again ratio distribution and integrated ratio distribution, which does not depend on the binning. So you find good agreement with Poisson. And also for the quantum billiard, you find good agreement with Poisson when you use such rational ratios. There you don't see these gaps. If you choose it irrationally enough, then you don't see any gaps like in the previous example. And here for the symmetry projected ones, here you have two symmetry, L equal to 0, L equal to 1. For the rectangle, you find again semi-Poisson, like in the square billiard. That is symmetry, separation into symmetries, then in all cases, independently on the ratio of B over A leads to semi-Poisson. So that is, it's as if you take out every second eigenvalue from the eigenvalue sequence of the corresponding full neutrino billiard. As I showed, this is Poisson, and it's more or less fulfilled. I mean, you will see some, when you look at the sequence of eigenvalues of your neutrino billiard and mark now those which correspond to L equal to 0 or L equal to 1, then you will see some changes, but it seems to be similar to taking out every second eigenvalue of a Poisson series. So these are just numerical results. And I still need to prove this analytically. So, and here, this is a symmetry reduced billiard, would be a triangle. That is, you cut along the symmetry line, then you get rectangular triangles. Here I show one example. They have a structure, seem to have a structure which shows how they are reflected, the waves are reflected along the boundaries. These are special examples. This is one where you have more or less a distribution over the whole area of the billiard, and these are the corresponding currents. And when you look at the momentum distributions, you don't see any peaks, so they are essentially kx and ky are distributed over the whole circle in that case. And here I show some, they also have scars. So scarred, I don't want to call it scars, but scarred wave functions. These are wave functions that are strongly localized along where is it? Along periodic orbits like that one here. So these are scars that Bogomolny, he studied them intensively for the corresponding quantum system, and you also find them in the neutrino billiard. So, and generally concerning triangles, I mean, Martin already spoke about it yesterday, because triangles, also quantum triangles, these are not typical quantum systems with integrable dynamics, but they have weird properties, so they do not necessarily have Poisson. And this depends on the angles. So I just looked at right triangle billiards with inner angle alpha equal to pi times pi over n. Then you have an integrable one. I mean, this is a 45-degree billiard, or you have the half an equilateral billiard or equilateral billiard. They have this property that alpha can be written as pi over an integer for all angles in the triangle. You have other triangles where the angles can be written in this form pi times m over n, where m is not equal to 1 and n and m are incommensurable. That is, you cannot find a common divisor. And these show are pseudo-integrable, and they exhibit an intermediate statistics. So one example for intermediate statistics would be the semi-Poisson statistics, which I showed. But it does not imply a semi-Poisson if you have a triangle with these properties of the angles. You can find it in some cases, and I looked at some cases which have these properties, but you can also find different properties. So it must not necessarily be semi-Poisson, it can be something. Semi-Poisson here means also, intermediate means that what you also have in semi-Poisson is that for S spacing 0, it's 0, the nearest neighbor spacing distribution when you look at intermediate statistics. So there you have the same property as for a chaotic system. However, when you go to large spacings, it doesn't fall off Gaussian-like, like the Wigner surmise, but like an exponential, like e to the minus s. So therefore, intermediate statistics, because it essentially has properties of a system with chaotic dynamics at spacing 0, and properties of integrable system, which would mean exponential decay for large spacings. There are also analytic expressions were derived by Attas, Bogomolny, and I think Giraud. I don't remember the other authors. So they derived expressions for the nearest neighbor spacing distribution. So for nu equal to 1, you get semi-Poisson. Nu equal to 2, nu equal to 3 gives your quarter Poisson. Quarter Poisson means that you take out first every second eigenvalue from Poisson, then you get semi-Poisson, then you take out every second eigenvalue from from semi-Poisson, then you get quarter Poisson. This is exactly what I found in the spectral properties of triangles, as I will show now. And here's the analytic result for the corresponding ratio distribution. So here I just show results for a triangle with B over A equal to the golden mean, and B over A equal to 2. So B over A equal to 2, it's just one side has length 2, the other 1, for example, and there you find interesting properties. So when you choose the golden mean, then the quantum billiard, which is shown here in green, it's close to semi-Poisson, and the neutrino billiard is close to quarter Poisson. So this blue curve is this analytic result, which was derived by Attas and Bogomolny, and others. So there you find agreement with quarter Poisson. This I found for when I used 5,000 and 10,000 eigenvalues. And of course, to prove that it's really quarter Poisson, one would need to, the best would be to prove analytically, because these triangles are very special. So it's extremely difficult to make any statements concerning spectral properties, because they really depend on how many eigenvalues you use. So, and these are, so this is for the result with B over A to a golden mean, and here I have B over A equal to 2, And then you find for quantum billiard a very good agreement with GOE. And for the neutrino billiard, you find very good agreement with GUE in this case. So it has properties of a system with chaotic dynamics. And this has to do with ergodicity. So, I mean, this is, these are billiards that were considered by Casati, and he could map them to a two-body motion and could explain this behavior essentially for these cases. But I don't go into detail. I mean, triangles, it's a big chapter. So these are non-typical systems with very interesting properties. And the properties depend on the angles, whether they are completely irrational or some rationals. So you have something pseudo-integrable or chaotic. You can have everything. So now I come to a next example. Yeah, okay. So this is a sector billiard. So neutrino sector billiard, 1/2 circle. Semicircle would be a sector billiard with sector, circle, circle, sector billiard. So when you look at the quantum billiard, you can find this, the eigenfunctions, which are given in terms of the Bessel functions. The Bessel function index, it's now not an integer anymore, but it's given by essentially by the angle, this inner angle, and the eigenvalues are obtained from the zeros of these Bessel functions. So the solutions can be written in this form. I mean, this one, as you can see here, it has to fulfill Dirichlet boundary conditions along this line. It's fulfilled for phi equal to minus alpha and phi equal to plus alpha. And along this line, it's fulfilled with this condition here. So you can find all the eigenvalues, all the eigenfunctions for quantum billiard. However, when you look at the corresponding neutrino billiard, you find something completely different. Also, when you look at the graphene billiard. So these are results for sector-shaped graphene billiard. In the vicinity of the bend edges, you find exactly the same results as for quantum billiard, because I mean, this would be the non-relativistic part in the eigenvalue spectrum of a graphene billiard. When you go now when you come close to the van over singularities, then you will find something between Poisson and GOE. So these curves can be described by the ensembles which were introduced yesterday by Thomas Guo, so that you have one Hamiltonian which is Poisson plus alpha times the Hamiltonian which is purely GOE. So these statistical properties can be described by exactly that ensemble. So this is a mixture between integrable and chaotic. When you now come to the Dirac point, there you will find wave functions which look completely chaotic, and also the spectral properties are very close to GOE. And that was the reason why we looked at the properties of the corresponding neutrino billiard. So here I show, first of all, results for the circle neutrino billiard. When you take the full circle, then you find Poisson. Also, when you take the circle billiard and you can separate it by rotational symmetry. So here I just show the results which you obtain when you just consider wave functions which have a threefold symmetry. Then you find perfect Poisson. Here, delta function, perfect Poisson. Here you always see these deviations in number variance, but also for the nearest neighbor spacing distribution, you find perfect Poisson. And this violet curve, it's obtained for the corresponding neutrino billiard. So this is the neutrino billiard, and then the brown curve is the result which you obtain. And then you now subtract the diameter orbit. Then you obtain perfect agreement with GUE for the, I mean, not in this case, yeah, you get perfect agreement with GOE in this case because you have an additional geometric symmetry. So for a neutrino billiard, you expect GUE if there are no additional symmetries, whereas here you always have the mirror symmetry with respect to the central axis. So then, so for the full circle neutrino billiard, you can determine the eigenfunctions. They are given in this form, so they are similar to what you get in a quantum billiard. And the boundary condition is that Jm of Kr should be equal to K times Jm plus 1 of Kr. So these are the boundary conditions. I mean, in the quantum billiard, you have boundary conditions that Jm of Kr is equal to 0, where R is the radius of the circle, whereas here you get a relation between neighboring Bessel functions. So for psi1, you get the Bessel function with index L, and psi2, the corresponding second component, it's given by proportional to JL plus 1. And these functions you obtain when you apply the boundary conditions. So here I show general results for the half-circle neutrino billiard for increasing mass. So for 0, you have agreement with GOE, and when you now increase the mass from 0 to 100, then you move closer and closer to the spectral properties of the corresponding quantum billiard. That is, in the non-relativistic limit, it behaves like it should behave, then the properties become equivalent to those of the corresponding quantum billiard, essentially. However, when you, for the massless case, you find chaotic behavior, even though the shape is the shape of an integrable billiard. So, and to understand that, one needs to look at semi-classical properties, and this would be in terms of Husimi functions and length spectra. Because this is, at first it was not expected, but then we saw in graphene billiard these properties, and then also in the corresponding neutrino billiard. Here I show some currents. I mean, you find currents which are scarred along some simple orbits, but you can also find some where this looks completely chaotic. And an interpretation for finding this GOE is that at these corners you have a coupling between the boundary conditions along that line and along that one. And this, due to this coupling, you cannot write down an analytic expression. So it's like in singular billiards with corners where you get some intermediate statistics due to corners, essentially. So it's comparable to that one, to the non-relativistic case where you have corners. So to look at the semi-classical limit, we looked at length spectra. There we used the semi-classical approximation in terms of periodic orbits. We also looked at Husimi functions. I introduced Husimi functions 2 days ago, when I spoke about the constant width billiard, and you can also compute Husimi functions for neutrino billiards. There I simply replace the wave functions by the first and the second component of the spinor eigenfunctions. So both separately, and both give the same result for the Husimi distributions. So it's again done in Birkhoff coordinates. That is, one coordinate is the parameter S, the length of the parameter up to the point of impact, and theta, P times sinus theta, P is equal to sinus theta. So it's like in the corresponding quantum billiard. And this I don't need to explain again, so I used also the trace formula, and then, for example, here I show some results for the half circle and quarter ellipse. In the quarter ellipse, you find exactly the same as in the circle. You find GOE. When you look at the quarter ellipse, it has classically, it's integrable. In the corresponding quantum billiard, you find Poisson. When you go to the neutrino billiard, then you find GOE. And here I compare the semi-classical approximation for the trace formula for half circle and quarter ellipse. Here shown as the fluctuating part of the integrated spectral density. And to obtain these trace formula for the neutrino billiard, I used Martin Sieber's result. He has an exact analytic expression for the trace formula of the quarter ellipse, of the half ellipse. You can extend it to the half circle, and these are very complicated ones, but they look very complicated, but agreement with the predictions is very good here. The lower part is a quantum billiard compared to the red is a theoretical trace formula, and black is obtained from the eigenvalues of the corresponding quantum billiard. And this one is a neutrino billiard, and you can see that peaks are missing, and these are exactly peaks which correspond to an odd number of reflections. So, but In all, when you, I mean, as I showed to you, when you look at the spectral statistics of the half circle, you see this chaotic behavior. But when you look at length spectra, they agree well with what you would get for a quantum billiard. That is, there you only see contributions from the integrable part. So these are don't help when trying to explain the chaotic behavior. And here I show Hosimi functions. So again, in the PS plane, momentum P is obtained by taking the angle here with respect to the normal of the trajectory, and S is the location of the trajectory. So this is, I mean, when you look at the non-relativistic case, this is a quantum percolarized surface of section, and we just used it and checked what does it look like when you look at a neutrino billiard. So here I use it for mass 0. Here you don't see any structure in the wave functions, and also the Hosimi functions here look completely different from what you see here. But in all, they don't look like what you would expect for a chaotic system. For a chaotic system, you would expect that they are distributed over the whole accessible part of phase space. So, but and when you increase the mass, then you will move more and more towards Hosimi distribution for the corresponding quantum billiard. So there's a non-relativistic limit also works. But this does not help to explain why we see GOE, and so the interpretation is that it comes from these corners where you have a complicated coupling between boundary conditions along this curved line and along that one, like in pseudo-integrable systems. Here I show the properties of the 1/4 ellipse. I mean, for mass 0, you have very good agreement with GOE, and when you go up, you move more and more towards quantum billiard. So, but this is just I wanted, so wave functions, so I wanted, I don't have much time left because I want now to come back to the constant width billiard, about which I spoke 2 days ago, about quantum dynamical tunneling, and I will show to you that you don't have it in neutrino billiard. I mean, this is just reminder. I mean, it's a unidirection, has a unidirectional dynamics. That is, when you start with a trajectory in one direction, then it will always move in the same direction. That is, when you look then at the Poincare surface of section, only the upper part is filled or the lower part. And you have, I mean, for that choice of boundary, you have small islands in the chaotic sea. You have an island along the diameter orbit and with Poincare modes. So this I explained already last time. So, and just to remind you what we found, I mean, when you take a quantum billiard, the spectrum can be divided into singlets, which correspond to diameter orbit, and these are not split into doublets and doublets, so singlets. Yeah, these can be determined. The eigenvalues corresponding to singlets can be determined from the eigenvalues of the diameter orbit of the circle. This is exactly, you can do it with the singlets for the neutrino billiard and also for the quantum billiard. So in both cases, you can find them by looking at the, comparing to the eigenvalues of the corresponding diameter orbit. These are J0 Bessel functions in the non-relativistic billiard, and in the neutrino billiard, you also have to use the J0 functions, and these yield the eigenvalues which correspond to the diameter orbit. And these can be separated. In a quantum billiard, you will have splitting of degenerate eigenvalues, eigenvalues that are degenerate in the circle billiard, because there you have some rotating in that direction and the other one is rotating in the other direction. And this is separated when you come to a constant width billiard, and they are just coupled via dynamical tunneling. But you will see a splitting which comes from this dynamical tunneling that will lead to a small splitting of the nearly degenerate eigenvalues. And in a quantum billiard, you can just separate by finding all these doublets and then separating into left doublet partner and right doublet partner. And then when you look at spectral statistics, you won't see any deviations. I mean, usually one would, if you separate two pairs of eigenvalues into pairs of sequences, then you would see missing levels in the full system if they are coupled. But they are not coupled in the constant width billiard. Therefore, you could simply separate into the two duplet partners. And in a neutrino billiard, I mean, the eigenvalues of the corresponding circle billiard, they are not degenerate. So there you don't have the symmetry properties. So you don't have any degeneracies. However, there you can separate them by looking at those Himi functions, because as I will show now, you will find Hosimi functions which are either localized in the upper or the lower part. This I show here. I mean, here again, what I showed last time for the quantum constant width billiard. So when you look at the quantum Poincare surface of section, it has contributions for p larger than 0 and p less than 0, which this is explained by dynamical tunneling. But when you look at the corresponding neutrino billiard, then they are either localized above for p larger than 0 or below for p less than 0. So now what I did, I separated into, first of all, diameter orbit you can take out. So the fluctuating part of the speckle density doesn't show any changes, so there are no missing levels. It's not missing any levels. That means that they are completely uncorrelated from the rest. And the rest are separated by into eigenvalues which correspond to Hosimi function, which is localized below at negative p, and some which are localized above. So this is possible in that case. Here I also show the result when you, as I mentioned already, here's the boundary condition which I wrote down in the beginning. I mean, I wrote it down only for mu equal to +1. But you can also write down this boundary conditions with here -1. So either you say psi2 is equal to k to the -1 e to the I5 psi1, as I wrote down, or you can also use mu equal to -1. And this I did here now. So here I computed the eigenvalues for mu equal to 1 and for mu equal to -1. Then you can see that when these are, the eigenvalues are identical, but the Hosimi functions are localized above when you choose mu equal to -1, then they are localized below for mu equal to +1. Or here this one is localized at negative p and this at positive p. So you have a clear separation between these eigenstates which correspond to localization at positive and negative p. And the spectral properties are the same as for the non-relativistic case. So the green is non-relativistic case, red is a massless neutrino billiard, and the turquoise is this random matrix model which we use to describe the spectral properties of constant width billiards, which are introduced already last time. So it also works for neutrino billiards. So you have here a GUE matrix for H because the spectral properties are expected to correspond to GUE for unidirectional system. And you have then around the diameter orbit, you have these integrable islands, and the coupling between both comes via these matrix elements. So here I also show length spectra. I mean, I also evaluated spectral properties for massive constant width billiards, but then you see again the transition to the corresponding quantum billiard. So these are not really new results. Also, length spectra evaluated for massless and massive ones, and here I just show the case of a massless neutrino billiard. Here, this is a quantum billiard. It has a very high peak, which corresponds to exactly this very small island in the chaotic sea, which we only found after computing Hosimi functions. And when you look at the neutrino billiard, it doesn't have this peak. I mean, these are 11, not 11, but 11 bounces at the boundary. So an odd number, and you don't see it in the length spectrum of the corresponding neutrino billiard. But you see its effect in the spectral properties, and also you find it in the Hosimi functions. So here some peaks are missing, and these peaks correspond to orbits which have to the length of periodic orbits with an odd number of reflections. I think that's it now, yeah. Okay, so if you have questions, I can come with a phone micro. Okay.
Thank you for the lecture. So you presented the semi-Poisson and the quarter Poisson distributions with like blend properties from chaotic behavior and integrability.
Exactly, yeah.
And yeah, could you talk a little bit more about the intuition behind it? Because I would think that one side you have chaos and the other side you have integrability, and I would believe that it would be like a continuum between them, but the semi-Poisson seems to be a robust behavior and universal.
Yeah.
So could you talk about the intuition
behind
it?
That's what already Martin mentioned yesterday. I mean, because when you have corners, then you will have not one torus, but you will have two tori, and at the corners, the system decides whether it goes to one torus or to the other one. So you will have, and the dynamics is not integrable anymore in a certain sense, because at these corners, for example, in a pseudo-integrable system with these pi times n over m corners, you get constants of motion which are not in involution. So you have a singular point in phase space where you don't have the properties of an integrable system. I mean, classically they are of measure 0. But when you come to quantum mechanics, then you feel them, even like with the bouncing ball orbits. You also don't see them when you look at the classical dynamics, but when you go to the quantum case, you see them. Or these very small islands in the chaotic sea and the constant width billiards. You don't see any effects from these small islands as long as you look at the classical dynamics, but when you come to the quantum case, then you see really big changes.
Also, since you mentioned the corners, like that scar weight functions that you showed it, they also have to do with the corners, right? They seem to to be...
Yeah, exactly. You get these, this is something that Bogomolny, he worked on a long time, so it's quite complicated. You can use certain models to simulate them, and this I cannot answer in one sentence. I recommend you to look at, he wrote just maybe a few years ago, a very detailed paper on these properties. So also about pseudo, these super scars, for example, do you have them when you, in the barrier billiard, when you have like a barrier billiard, then you find these super scars, essentially. These are very highly localized states, and this comes from this diffractive corner here. For example, or when you take a billiard, and you just put in a delta function potential, then you will also have, I mean, and when you look at the Poincare surface of section, it will be everywhere integrable except at that point where you don't have the constants of motion and involution. So these are singular points, essentially. And when you look now at the quantum dynamics of the quantum spectral properties or at the wave function properties, then you will immediately find deviations from Poisson and this intermediate statistics, essentially. So that's what he was looking at in detail for this example, also for triangles, and it's a complete chapter. So it's not possible to answer in one sentence, but...
That's okay, thank you.
Okay. Yeah.
Thank you. Thank you for your talks. I wonder, has anyone looked at, for instance, the fractal structure of the wave functions along the borders for the different, has it been done?
Yeah, this is exactly what has been done as in the context of pseudo-integrable systems. I mean, there are works that use boundaries which look like that. You have a boundary which looks like that.
Yeah.
With irrational step sizes, and there you can study also, and there you find also the intermediate statistics. So this has been dann, ja.
Yeah, yeah. All right, thank you.
More questions? Oh.
Thanks for the talk. There was a slide when you show us the quarter quantum Wheeler.
Also, yeah.
And I was wondering, because if I remember that the distribution was a Poisson one, but the quarter quantum Wheeler only has like the conservation of energy, but it's not rotational invariant, so you not have angular momentum.
Yeah, it's symmetry reduced because you cut along the symmetry lines, yes.
But why is Poisson and is not supposed to be like a Wigner one? If you have a quarter of a Wheeler of a...
No, this depends on the system. I mean, if you take an ellipse, then you have two constants of motion as long as you take half of it. I mean, you have two constants of motion for the full one, and you have two constants of motion when you take half of the ellipse and 1/4. But if you take just 1/3, for example, then you will have a chaotic dynamics.
But in that case, so you don't have a continuous symmetry in the quarter or in the...
You have this, I mean, when you have an ellipse, then you have two focal points, and the product of the angular momenta with respect to these focal points is a constant of motion.
Okay.
And you still have it when you can show by symmetry considerations that you still have it when you cut like that, because this is like Dirichlet. So you take just the symmetric part. And this when you cut along that line, then you take just antisymmetric ones, those which are antisymmetric with respect to this line and with respect to this line.
Okay, okay.
So
Yeah, I get it.
Therefore, you still have the...
And the other question was, in the last slide, when you show the momentum distributions for the quantum Wheeler and for the neutrino Wheeler, there was one that you have the both peaks in the quantum case.
Momentum distribution. Yes.
Both peaks in the quantum case.
I can show. What
yeah.
Oh, I have it here.
Yeah, that one. So, and in the neutrino case, you only have a peak either centered on the right or on the left. That means that you have the ball is bouncing only one direction.
Yeah, exactly. You don't have tunneling. I mean, it behaves like a classical system.
And that is only because the normal boundary condition that you impose in the building.
Yeah, it has to do with the boundary conditions. Yes, these boundary conditions forbid that you turn back.
Ah, okay. Thanks.
So, I mean, it was not expected, this result, but that's the result that we obtained, and I mean, the reason must be the boundary conditions, because that's the only thing that's different. More questions?
In the random matrix theory model that you shown, how do you know how many the dimension of the matrices? Why 100 by 100 and 300 and 300?
I chose it such, I mean, this is one example. I mean, I should have erased it because it's confusing. But I chose the dimension of this matrix H, I chose equal to the number of eigenvalues which I had. And for the D1, I also chose a number which is similar to the one which we corresponding to the to eigenstates that are localized along these diameter orbits. I mean, you can look at the wave functions, and then I counted simply states which are localized in the diameter region, and then I just chose that number.
So when you diagonalize your matrix, do you plot every Husimi function of all the eigenvectors? Do you calculate the Husimi function of every eigenvector?
Yes.
Okay.
I mean, this goes fast. You first need to compute the eigenfunctions, but this is very convenient with this boundary integral method, because as soon as you have the eigenvalues, you can compute all the wave functions. So it goes quite fast. So the time-consuming thing is to find a complete sequence of eigenvalues, and this depends on the shape of the billiard. I mean, I was lucky for the triangles, it can be complicated in the quantum case, but in the neutrino case, since you don't have these near degeneracies, it's much simpler. So generally, it's good that there are not that many degeneracies, so also not when you separate by rotational symmetry classes, you don't have the degeneracies. Like when you do for the threefold quantum billiard, the states corresponding to L equal to 1 and 2, they are all degenerate, and you don't have this for the corresponding neutrino billiard. I think I forgot to mention. So there essentially you get 3 different spectra, whereas in the quantum just 2. So, oops.
Thanks for the lecture. I was thinking about that as there is a correspondence between the sublattice valley of a billiard made by graphene and the dynamics of a Dirac fermions, the chirality of fermions of Dirac.
Yeah, I mean, you have the spinor structure, so in the graphene billiards it's called pseudospin.
Yeah, yeah.
And in the neutrino billiard you have exactly the same. You have these spinor components, psi1 and psi2. And we try to, to get any explanation, because we don't find what you find in a graphene billiard. You always have the GOE statistics, whereas in the neutrino billiard you have GUE. So, and the interpretation was that it's simply only, if at all, describable by a massive one. And there you have, this is like coupling the 2 spinor components.
Okay, so even if we analyze a graphene billiard, in the random matrix model, we use ensembles, Wigner dice ensembles, not the Kiro ones.
Yeah, we don't use them, yeah. We only use essentially 1/2, because when we don't use the 4-dimensional Dirac equation, but we use only 1/2. When we do these measurements, we only get essentially 1/2 of the graphene billiard.
Okay, thank you.
This we cannot do, at least not in experiments.
My question is not necessarily about the 2D electrodes, okay? My question is not about the 2D electrode necessarily. Is okay?
Yeah, I'm not sure whether I can answer it.
What the seminal paper of Borrigas, Janon, and Schmidt did more than the previous works of Berry and Cassati, because almost all literature do not cite these previous works. The Borrigas, Janon, and Schmidt seminal work of 1984.
Yeah.
What did do more than the previous works of Berry and Cassati?
Cassati, he was the first, and Berry also, I think either Berry or Cassati was the first. They just mentioned in one sentence, hidden in a paper which was published in an Italian journal, that they have the suspicion that it behaves like random numbers of these Gaussian ensembles. But Borrigas, Giannoni, and Schmidt were the first to explicitly state it in a PRL. I think that was the main problem. I met Cassati many times, and I talked with him about it, and he was a bit upset because everybody always only, so whenever you cite BGS, you should also cite Cassati and Berry. So that's what I'm doing now. And
it's okay, thank you.
So the problem is that that they publish a PRL, whereas Cassati published it in an Italian journal, which is not well, it's not internationally, not, I know it well, but not everybody. So, more questions? No, so then we can have a break, and then we start at 11:30 with Thomas Guhr.